general relativity, step by step. Last time I made the observation that delta S squared, which is the squared interval, is invariant. So what that means is that if I calculate this thing here, and that's a minus delta t squared plus, let me just pinch in a bit, make my writing a bit better, delta S squared equals minus delta t squared plus delta x squared plus delta y squared plus delta z squared. I can calculate the same thing in a barred coordinate system with t bar squared, delta x bar squared, delta y bar squared plus delta z bar squared, and these are in fact the same quantity. And what basically that means is that the metric tensor that we use here, this metric tensor here, is invariant. It's not invariant, it's just that we can use the same one and get the same answers in the different coordinate systems that we choose. So I'm going to figure out what delta S squared is. And delta S squared, well, it can either be 0 or positive or negative. You'll notice that there's different signs here. There's a minus and a plus. The individual quantities in here are always positive because they're the squares of things. But there's a minus, some are negative, the first one's negative and all the others are positive. So depending on the relative sizes of these guys here, we can have delta S squared can either be 0 or positive or negative. And of course, while I'm talking here, we're using this negative sign first and then 3 positives. We could just as easily do it the other way, and that would mean that the sign conventions are the opposite way around. So if we think about what delta S squared equals 0, that corresponds to motion along a light curve. So that is what we call light-like. And again, I keep on having to say it, but I'm going to say it over and over again, that if it's light-like for one observer, it's light-like for all observers, because delta S squared is the same quantity, or it's calculated as the same value for all observers. If delta S squared is positive, what does that mean? That means that delta S squared equals minus delta t squared plus delta x squared plus delta y squared plus delta z squared is positive. So I guess the standard way to do that is to arrange things so that delta t equals 0, and then what we've got is this nice system here. I'm going to choose a coordinate system t. I'm given an event E1 and an event E2 which occur at the same time as measured by this particular observer here. And of course we've got the delta x squared is positive, and we've got other positive terms as well. And we call this a space-like interval. Space-like interval. Defined by delta S squared is positive. Now of course some guy could be in his spaceship, which I'll draw here. Where's my blue? There it is. There's Mr. Astronaut in his spaceship cruising along at some big speed here. And of course when he measures it, his coordinates look like this. That's his space coordinate, that's x bar, I guess in blue. And there's his t bar. Oops. T bar. So measured for him, you see this time here is above the axis, and the time of this event is above the axis, is positive, and this one's negative here. So for the blue person, delta t is not equal to 0 in the blue person's coordinate system. However, we know that delta S is still positive because it was positive for the black coordinate system, so it's going to be positive for the blue coordinate system because delta S squared is the same in all coordinate systems. So if one observer sees this quantity, or sees two events being linked by delta S squared, if delta S squared is positive for one observer, it's positive for all observers. And because in this special coordinate system here, which I've drawn in black, that looks like a pure space displacement. There's no difference in time between those two events. They occur simultaneously for this guy. How can I show that? I guess I could. Person in the black coordinate system could send out some photons and observe that those photons arrive at both of those events at exactly the right time. So as far as the black coordinate system is concerned, that's a space-like interval. And all observers will agree that that is in fact a space-like interval. And of course the other one we've got to deal with now is delta S squared is negative. How did I define it now? I've got to look back each time. I'm saying that delta S squared equals minus delta T squared plus delta X squared plus the other two. And if that is negative, then the prototypical example of that would be E1, set up some coordinates here, that's T, that's X, and here's E2, and I'm interested in the distance between, or the interval between E1 and E2, and that's going to be minus delta T squared, which is negative, of course. And we call this a time-like interval. And of course, I can transform to the units or a coordinate system appropriate for a little person in his spaceship here. Bong, 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 bong. And I'll draw the blue coordinates in there like that. And of course the blue person says that these two, that's his X and that's T. The blue person says that these are not the same position in space because they're moving relative to his x-axis, to his t-axis. But because delta S squared is the same for all observers, we all observers agree that the interval is negative. And so it's a time-like interval which is not dependent upon your particular coordinate frame that you observe it in. And that's why it's an interesting quantity. And we'll use this over and over again in relativity. Okay, so let me just summarize that. Oops, I'm still in blue. Let's go back to black. Delta S squared. 0, positive and negative, like. Negative was time-like. It's very easy to get these the wrong way around, especially because a lot of people use different sign conventions. I've just put the negative one first and the positive one's there later, but other people do it the other way around. So it's very easy to get these wrong way around. This is space-like. Okay, so three different ways of viewing the three different types of interval. And of course, if delta S squared is positive, then I will say that it's space-like, and I'll say the actual distance equals the square root of delta S squared. If delta S squared is negative, then I'll say that the time difference is going to be equal to the square root of minus delta S squared. And if delta S equals 0, then it's just a photon path. Or the two events are linked by a photon path in free space. Okay, so I'm going to stop there. Stop.